we will have the recording for those that decided to take some holidays around the free day. So Bildschirmfreigabe, screen number 2. So today we will be taking a look on networking, since various applications require that. Often scientific devices have either a common port interface or a network interface, so it is very useful to be able to communicate with those. And we will take a look at first how to do that using Windows built-in APIs, and then next we will take a look how to do it with modern Qt based classes. So let's start a new project for that. Create new project, console app. Next, we'll start with a server and call it TCP server. That will also be the more complex part of the server client architecture. Okay, we don't need that. And let's take a look. First we need some includes. Wait a second, let me just quickly get the right headers for that. WinSock2, and we will need the right header file, if I remember correctly, as well. Sorry, not header, the right library. Linker input. Just need to look up the library name for that. It was something like vs2 underscore vs2 lib, I think. Usually this is done only once when configuring the project, so it's easy not to remember the right WinSock lib. That's the right name. Zack. WinSock2 32 library. Let's quickly see if it finds everything that's needed. Okay, and that works fine. So let's start. First we need to initialize the whole WinSock infrastructure. We specify the version of the WinSock that we want this to be, and we need one more thing. Okay, so once we've done this, we can start using the different sockets. So the socket API in the easiest form is quite similar to how it works on Linux. So it's not the basics are very similar. Only once you start to using the more advanced functions, the API becomes different. The reason was simply historical compatibility with simple applications. So first, what we need to do is we need to create a socket which will be listening on incoming network connections. So the way the TCP protocol works is that you can it is a connection-based protocol. So first you are opening a socket on which your server is listening on incoming connections, and as once a connection comes in, then a new socket object is created, which can then be handled by some client handling routine, and the server socket is listening for the next incoming connection, and it can in principle accept as many connections in parallel as it wants. On the user side, it is much more similar. You just open a socket, call connect, specify which host you want to connect to, and it creates the connection, or you get an error if the host is not available. The important thing about a connection-oriented communication is that your whole connection is treated like one continuous data stream. So you can send data and receive data, and when you receive them from your point of view, let's say packages, they will for the most part simply still arrive in the same order in which you put them into the socket. There is no possibility of the order of the data you wrote on the socket changing, or some of the data from your point of view or from the point of view of the application getting lost. Of course, on the network layer itself, this is not guaranteed by no means. So there you only have the IP protocol, which only sends out individual packages, and it does not ensure that they arrive or in which order they arrive. The only thing it ensures is that they either arrive at the right destination or not at all. And the TCP protocol is then used on top of the IP protocol to ensure that from the point of view of the application, you have in fact a properly ordered data stream. This is done by the network stack. It is part of any modern operating system, and you have there a complex mechanism which is breaking up the data stream you fed to it in individual packets, sending them out, keeping them keeping a copy even after they have been sent out, and they are then waiting for the other side to receive the package and send back an acknowledgement package, which tells the sender that the package has been received. Only then the package is removed from the sender's sending queue, and once this is done, the sender can then send the next package. Usually you have something called a send window, which means how many packages there can be in transit at any point in time. How the size of this window is exactly calculated is out of the scope for now. It is just good to know that such a thing exists. So sometimes you may have a better performance if you open a couple parallel data streams. So sending everything in one stream is not always the fastest method, but this is usually only relevant if you have very high data rates in excess of a gigabit per second. Okay, so now let's continue with our server. So first, as mentioned, we need to create a server socket. So let's do that. We call it listen socket. Then we need to use the function socket to actually create it. We have to specify to the function which communication type we want. It can be either IPv4 or IPv6. So standard is just INET, and the other would be INET6, which would be IPv6. But for our current test case, we will just use normal IPv4. Then we can specify a socket type, which in this case, as I mentioned, will be TCP. IP port TCP. Socket, wait, AF we have, type we have, sorry, one more thing we need to specify, whether it's a stream socket or a datagram socket, and since it's TCP, it's a stream socket. Sock. Now we have everything. IP. I have a typo. IP. IP port underscore TCP proto. I forgot though. Okay, so we have now our socket. A socket can be bound to either one or all network addresses that are available on your computer. So you will have one network address from your Ethernet card. If you have an Ethernet card and the Wi-Fi connection established at the same time, you will have two. If you have also a VPN connection, you will have 3 IP addresses, etc. Usually your system is just picking one, but you can specify using the bind command a particular address. In case of opening a TCP socket, you need this bind command to also specify which port you want to connect to, to listen on. So let's quickly do this. So before we call the bind command, as you see there, it wants the socket, of course, but then also a few other parameters which are not that simple. We need a socket address structure and a name and a length variable for how big the thing is. So the structure is defined in our IPsec header, so we can quickly take a look here into the definition. This is a very basic definition. There are more complex definitions available, and then you need to cast between them. So for our use case here, we'll just go with a other info. Now let's fill in all the parameters. So as you see here, if we go to the definition of this one, there are much more member variables specified on it. And the whole idea is that you can you have different structures depending on, for example, the protocol you are using. So there could, if you would want to connect and specify an IPv6 address, then we would use a different version of that structure. We can quickly look it up if we have one here defined. I think it should be defined somewhere, but we might need an additional header for that. So let's quickly see if we get info underscore. No, we don't have a. I guess we need another header for IPv6. We can take a look onto this in a moment. Let's first fill this out. Some of the data are redundant with what we have already said. Socket type, again stream, sock name punct IE protocol TCP. Then we can specify some flags, IE flags. Yep. Okay. Before we do that, however, we should also ensure that all the other flags are 0. So we use memset, memset 0, comma size of our structure, and we need, of course, to pass the reference to it, its address in memory, and not just its variable name. So we can now here pass it to it. So bind the name punct address, comma name punct adlen. Do we have everything? Let's see. doesn't it like? Yes. Okay. One more thing we should do is if we should probably get one of the addresses so that we are not just using any address, but we want to know which one we will be using, so we use get address info. No, I'm sorry, get address. Do we need another header for that? We might need another header for that, so hash include zack ps2tcp und Winsock2. Now we have Winsock2. Should we have now we have the thingy. Yeah, so the first argument can be null. The second argument will be our server port. Is that's not a none. Use our structure here, and we want the result into another structure of the same name, so the same pointer, comma, reference, comma, right here, and this one then we will feed our bind function. Okay, and now we can start listening on that socket. So it's of course the listen function, which just takes a socket, and we can specify to it how many pending not yet accepted connections the listening socket should accept. So let's go with, I don't know, 25. Much more than what we need for our test case, but why not? And what we also should do is we should check the return value of our various functions to see whether they actually succeed. So we can, for now, just write them to a variable. Then when we step through it with the debugger, we can check the content of the variable to see what's happening. Okay, so now what we will want is a loop, which will be just accepting incoming connections, in which we create another socket variable. This time we will call it client socket. Okay, client socket. The accept function as used here will be blocking until it gets an incoming connection. Using more advanced Windows APIs, what one could also do is to make the function non-blocking, so that we would get an event on which we could wait instead. That might be more elegant, but for a simple server this is already enough. Okay, so we have here our accepted connection. We can check whether the connection actually is was accepted or if an error occurred. So if socket is equals invalid socket, then something went wrong. So we can get the error from the last operation like this, and we will just continue. So we will just go back to the top of our loop and then continue with the next connection. Otherwise, we have our connection established. We can do something with it, and at the end we can close it and wait for the next. We don't have a break condition for our loop here yet, but just for completeness we should add also a close socket statement for our listening socket. In principle, once we are done with the application, we can also use the VSR cleanup function to deallocate all network related resources. But now first let's continue with our socket. So we start here again with loop. What we want to do in the socket will just be to receive data and then send them back like an echo on the terminal. And then we will connect with a telnet client to our server and see how it works. And once this works, we will then create just a client in another project and let them communicate. The next step after that would be to make the whole thing a bit more sophisticated, for example, by starting new threads to handle the client connection, such that the server can keep listening and accepting other clients. Currently, the way it is done here, it can only then effectively accept the next connection once it is done with the current connection. So this is not something you would want to do this way outside of just some proof of concept code. Okay, so let's continue. We will be receiving data using the redsv function. It again wants a socket, so this time it's our client socket, of course. And then it takes a buffer where to store the data. So we will need first of all a buffer. So let's go with buffer. Let's make it 4 kilobytes in size. Comma len is, can use the size of command, and we don't specify any flags. We also want to know how many bytes have been actually received into the buffer. So that's the function receive will return to us the amount of bytes received. So if this is less, if this is more than 0, then it was successful. If it is 0, then no data have been received, and if it is less than 0, then an error occurred. So we can also handle that case. We will not care for the case if the data is actually 0. So this is less than 0, then red is gleich VSR get last error. As said, we are not printing the error anywhere, and continue. We just want to read the return codes into a variable so that oh, I reused that already. Let's rename this variable then. I just want to be able to see the return codes in the debugger. This is usually useful. We could of course look on the register, the RAX register directly, which would contain the return value even if we have not assigned it to a variable, but this way it is just more convenient. Okay, so in this case where we have actually received something, we can, as we said, we want to send it back, so we just use the send function. We can again specify the socket, we specify the buffer, and the length to be sent. In this case we need to take the length which we have received, as we don't want to send any garbage. So our buffer is basically filled with garbage, and only its beginning portion will be overwritten with incoming data. We of course assume that we will have substantially more incoming data, substantially less incoming data than what fits into our buffer. Currently, if we would have more incoming data than what fits in our buffer, we would require to have some additional larger buffer, or maybe a vector that we can grow and put as many data into it as we want. An important thing to keep in mind when using TCP is that, as I already mentioned earlier, it represents a data stream. So if you put data in, like in a chunk on the send function, it still at the receive function can come out as any arbitrary amount of smaller blocks. So your protocol that you will be communicating through that network connection needs a way to know when a certain higher level data package is completed. One way is to use special characters to denounce the end of a communication message. Another approach would be to just at somewhere in the header of your package write down the size of the remaining package payload. The first approach is kind of a bit old school. Nowadays you would just have a package format which contains size and is this way much more reliable. But for our simple test case, for now we are just sending text around, so this should be fine. As said, we have sent, and in principle we could check how much, so check the result of our send function, because this one also might be an error. And there is actually a special case where this error happens even when an error happens, even if as such nothing bad occurs. Namely, if the operating system buffers for sending are full. So if you are sending data to the other side, but the network is slow, or the other side is slow processing the data, then you will run in a situation where you won't be able to send any more data, and it will return an error with a special error code. What was it? These are busy something. I don't remember the actual variable name. Let's quickly look that up. It was something with busy. It's not in this header. One moment, please. I will look that up, then I can tell you. I think the hex value was 53. Yeah. And it would be good if we could explicitly error codes. That needs another include. That needs another include. No, then. And the actual value for the error code to look for if is VSA would block. Is that the correct one? Yes. So if we get this error, then in which case we would not want to abort, but instead we would want to just wait a short while and then try again. For the purpose of our simple application, we will not need to try a reset, since we will be only sending small amounts of data, and we want a quick demonstration. So let's now run our application. And of course the loop will then in an endless loop go back again, read the next amount of data that arrived. We need to allow it in our firewall, of course. Okay, we can check that it is in fact listening using a task manager, TCP server, sockets, and voila, it is listening at the port we wanted it to listen. So now to test that thing, I will quickly copy a small utility that we can use here. It's a command line telnet client. Suck. We specified a localhost IP address, since when you look here, it is listening on the local address 000. That effectively means that it's listening on all the addresses. So when creating a socket and listening to something, you have the choice either to make it listen on one specific address or on all of them. There is a special case where you can make it listen on two addresses at the same time, but this only works if the other address is an IPv6 address, which can be mapped to the IPv4 namespace. Usually if you would want to listen on 2 out of 3 random IP addresses on your system, you would actually need to open 2 individual sockets and listen on them individually. Okay, so we provide the port, and now we have a connection. You can also see here that we have an established connection between localhost and localhost, since we were here on the localhost, and here when we start typing, we see actually every letter I press arriving twice. The reason is that this particular tool has a local echo, so it's automatically duplicating. And as you see here, now we have it entered close wait, and it should be listening then for the next connection. We can quickly try it again, but this time let me use a different client. We just need to find out the IP for that. Sorry, not this one. Send there. With ipconfig/all on Windows, you can find out all your network adapters. In this case, it's only one, since it's a virtual machine. But on a laptop, as mentioned, you would have at least one for LAN, at least one for the for Wi-Fi, and probably some virtual ones as well. So now I will connect remotely with Telnet port 27015. Okay, this is our client, and now when we type, we only see it once because it does not. This version of the client, it's called PuTTY, does not have a local echo. And when we inspect our application, we see here that we now have a connection from 1070 1020 to 1070 1012. 1020 is the virtual machine, 1012 is my host on which I started the application. It's also why I can move it out of the out of the screen. And again, when we close it, then the connection will be closed. Okay. That said, now let's create an own client to connect to it. Create new project. Console application next. TCP client. Okay, so now go back to our server. We can look in the Solution Explorer and quickly copy our the required library name, so that we add it. If we would not add this library, we could not use all these various socket related functions. We would just get a linker error. Nope, cancel, that's not the right one. Input here. Okay, and let's see what else we can copy. I will just copy the whole project and then just delete what we don't need from the inside. So we still want to connect, probably don't need that. So again, we need to create a socket, but this time we will use socket, comma, name length. Actually, we should use, oops, right here that we can copy as well. And we put a breakpoint here and just quickly check, and we of course need to change this to client socket, just to check whether it will connect properly. Breakpoint and breakpoint. Okay. Okay, the debugger is loading some symbols. That will take a while. Okay, that returned as an error. Why did that do that? We got the, which was that again? 1 0. Right. Oops, that's a small oversight. Now it should work correctly. Yep, now it should also connect. Yep. So if we now inspect our client, first we see a established connection here, and then if we inspect the server, which is somewhere, where did it go? There. Again, here we see the connection, the kind of other end of the established connection plus our listening socket. So here now, what we of course could do is we could again send something on the socket. So send client socket, comma test, comma 4. Since we know how long it is, let's do it this way. And 0 for no flags, and then we want to receive it again. So we go to this part, this code, and we can copy this code. And once we arrive at the breakpoint, when we rerun it again, we expect our buffer to contain the string text being sent back to us from the server. What is it waiting for? It's waiting for something to. Let's quickly run it again. So we sent something, and this is waiting. We call. Why doesn't it terminate instantly? That should just give us the data from the server. This means the server is not sending the data back anymore. So let's quickly debug that scenario. So we are here, we send the data. The server somewhere put itself into a non-operative situation. Let's restart the server quickly. And then let's run the client. And it works as expected. We are getting our test back, and a lot of garbage stays in the buffer. We could in fact pre-initialize the buffer with zeros. That just looks nicer. Also, it's kind of good practice because if you have zeros, then the chance of something random happening is lower if you would misinterpret the buffer. Okay, so it seems actually that we somewhere have a small bug. We failed to accept the next connection. Let's put a breakpoint here. Restart the server, restart the client, because the first time it works fine. Here we get our buffer with test and 4 characters read back. We forgot to close the socket on this end, and the server was then stuck forever in waiting for more data. At some point it would of course time out. Close socket, client socket. At some point it would have timed out, but that would take a long time. This is also why it is recommended to use a separate thread to process the client requests instead of doing everything in one thread. Okay, so now we close the socket. It did not close it on this end. Did I forget something? No, theoretically. We can use the shutdown command to close the socket, to force close it, and just need to check what was the arguments that it takes as method. I think it doesn't matter, but I think we can go with 0, but let's check it. Okay, we need to specify the SD both flag and close socket. That should now we probably need to restart our server first. The client is starting. Okay, so this worked. Okay, for some reason our server is not properly getting notified when the connection closes. Well, one more reason to process the client data in a separate thread, so let's do just that. So after we have accepted the thread, we will create thread, null socket /0 start routine. Let's quickly look up the exact function prototype that is expected, and create our function for the thread. So that needs to stay. Let's call it client procedure, and as you see, it takes one parameter which will be passed from our server. So first of all, client procedure, then the param, and that parameter will just pass the client socket. Creation flag 0, thread ID null, we don't care for the thread ID. And we'll close the handle instantly, since we don't need to do anything else with it. We just need to cast this to LP void. Okay, now we take our function to our client procedure. We will need to cast to get our socket type back. Internally, this thing is just a OINT pointer, so we don't need to worry about losing some data when casting this way. If it would be a more complex structure, then of course we would need to create it with new and then just relay the pointer, but the way this works here, this is fine. Okay, so let's run it. And now what we can do, we can open multiple consoles and one more. What was the port? Here we have it. Suck. And have one connection, and at the same time have another connection, and both are working just fine. What we of course could also do is we could connect them so that whatever comes in one comes out on the other, but that would require some additional logic to handle the case while only one connection is established, so we don't need that for now. And since that was already about an hour of me talking, I want to ask you, do you have any questions about this general socket communication? As I mentioned, the APIs for sockets, at least the basic ones, are the same on Linux, so at that point it's even somewhat platform independent. So do you have any questions about that? Okay, no one seems to have any questions, so let's continue. So what we will now take a look on is how to do the same thing but using the Qt API, which is a kind of much more convenient. It internally uses helper threads, so the whole program logic itself can be contained in only one thread and connected with signals and slots to the worker threads that Qt is using internally. Since we have already a nicely working server here, we can just run it and start this time from a client application. So we create a new project, zack. We go to a Qt console application this time, so that we have all the different Qt classes available to us. We call it QTCP client. Oops, it didn't type. QTCP client, zack, create. Ah, shit, I created it in the wrong folder. I think I created everything in the QWT folder. I will need to move those projects out later, but for now it's fine. We don't care where we save it. I just need to clean it up later to be where it has to be. Okay, so we have this. Now we need to add a component to our Qt. Qt projects. Yep. Here, modules. We need to select the network module. Qt, what was that? Network. And we don't need to add a library manually because that is kind of done automatically for us by Qt. So the nice thing about the plugin from Qt for Visual Studio is that when you add new Qt modules, it will automatically add the required libraries to the project, as well as the required include directories, so that you really just need to include your individual header files in the project without having to worry where to find those include files. Of course, with the normal Windows headers, this is not a problem, since these directories containing them are included by default as well. But for now, for this example, we will be using Qt, so let's include Qt core QTCP QTCP socket, and QTCP socket. Let's call it socket, and punct connect. Connect to host. The qhost address can interpret a address as string, so we can use that, and we need to specify the port again to which we want to connect. Zack. Yep. And once this function is out, we should already be connected. One thing that is quite nice with Qt is its use of signals and slots. So we can in fact improve this by creating an own class for that. So let's create a class. It's a client from type QObject. Oops, that's QObject. Zack. And then we will put our socket into that object and see how we can connect it. So this we will need later. Hash include C client. Let's create a new client instance. QObject. We need our constructor. And our socket. We need to include as well. Okay. So we go to our client, zack. and connect our socket. But before we do that, we'll connect a few slots. So here private slots, void on connected. The slot will be signalized once the socket said that it connected successfully. So socket connect signal. What was the socket? Signal is the connected signal. Connected, comma with this comma slot was unconnected. The name for the signal must always be the right one as defined on the object which is sending the signal, but the name for the slot on our own object we can pick a name and then we just need to stick to it. Okay, so here once we have the connection we will write to the socket our test string, and of course we would also want to read the data back, so we will take a look what other signals we have. We have, for example, so here we only have socket specific signals for the signal which will be signalized. Once we have something to read from the socket, we need to read to look onto the parent object of our socket. It's the QIO device, which is also the base object for files. So in Qt a lot of the I/O can be done very similarly. And here we have a ready read signal, which is signalized when there are data on this object to be read. So we want to connect to it, and we'll give it a name on data on our end. So we will of course need to create our slot. We also need to create it in the header, of course. Okay, qdebug. We need to include qdebug. Hash include the qdebug. And now we just read everything from the socket. Read all. So what we expect when we run it is simply that it will send test and then receive test back on the console from the server. Yep, as you see, it works fine. We can maybe step through it in a bit more of detail. So we will put a breakpoint here. Let's do the breakpoint there, because here we just get that nothing was received. So when we run our application again, then here we arrive with some data received. As you see here, there is not yet anything in the console, and when we move this so that we see our other console, as soon as we step, so here we are in the line with the sensor. As soon as we step past that line, we have received our message back from our server. Okay, so let's stop that. Also here, let's break the loop in case of an error. Instead of continuing, here for sending we will also break, unless it was the buffer full, in which case we just ignore this one package and continue. Good. And now the next step would be, of course, to implement a server in Qt. So let's quickly do that. Create new project. Qt core application. Yep. Qtcp server. T. create. Next, we can actually add the right network. What was it? Printing queue to data network here. We can add the needed component already here. That is maybe a bit more convenient. Okay, so like before, we will create a new class for that. We'll call it just server. Queue object public suck. We also need to include hash. Queue debug, so that we can put things to debug output. Then here, here, the server. Create a new object of our server, and inside the server we will work in a similar fashion. So, listen. Here we want the any address, so we are lazy, we just copy it from here. And we will specify a port, which was the last time here. Yeah. Suck. Okay, and before that we of course want to add some slots. So we quickly take a look on our server object, which slots, which signals it signalizes if there is an incoming connection. So we have here this one, a new connection. This gets signalized each time a new connection is received. We don't need to specify here a backlog size or other things. There are some defaults that Qt picks automatically. We could change some parameters on our server if we would want it to, but we don't have to, so let's don't do that. On a new connection, void on a new connection will signalize when we receive an incoming connection. Connect server, comma, slot, sorry, signal on new connection, comma, this slot on new connection. Okay, and now we need to make basically the accept state of our operation. Okay. Pending was pending. Next pending connection, and this returns us a CTCP socket, a QTCP socket, which already is ready to be used. So here we can add a list of sockets. Cool map. Let's do the QSet, since we don't really need to associate anything with anything else. QTCP socket. Sockets. At this point we would have two options. You could either create an own client object that would represent an incoming connection. And the second option which we could do is we could just do everything on our server client, and then server object, and then just look from where the individual signals are coming. I think for simplicity, let's go with that approach. So we will need to add some more signals, some more slots here. So one will be void on disconnected, which will be notified when a socket disconnects, and we need one on data, which will be notified whenever data has been whenever data is ready to be received. So let's quickly add them here. Okay, we need to add here the new socket q TCP socket to our set socket sockets.sockets.insert socket, and of course we need to connect it with the two new oops, not here. So we have our socket. Since it's a pointer, we don't need the end. And one will be disconnected. So let's quickly okay, we need to include that explicitly. That's from abstract socket. Disconnected, suck. So disconnected with our on disconnected, and how was the other one called? Ready read. Okay. So if the socket gets disconnected, we need to know which one it was. And luckily Qt offers us here a function called sender, which returns to us the pointer to the object which was the sender for this particular event. So if we have multiple sockets, as we can have connected to the same slot on the same object, we can still tell them apart by looking up which object was the sender. In this case, we don't need to do much except to remove it from our socket set. In theory, we would not even need to cache that socket set if we just want to replay data, so we could do that completely without it, but it is good practice to somehow keep track of your object. Also, we will delete later this object since it's no longer needed. And on data, we just will again resolve the sender object and then call on it the read all function, which returns everything that's in the buffers until now, and we can send that back by socket write data. Okay, let's start our server. We will again test it with the telnet client first. Did something complaint? Okay, wait, something didn't work out as it should. Why? I didn't change anything. It must have been some Visual Studio glitch. So it is up and listening. I need to check which port we used. I don't remember it by heart. This one, suck. And oh, damn it. I have a typo in the address. Let's quickly kill it. I somehow didn't hit the 2. And as you see, it works quite nice. So we can again have a breakpoint in our server. That's the wrong window. When we start something here, sorry, we want one line lower. In this case, we only get the G because I'm not typing fast enough. So if you would want to catch more than just one letter, then I would need to type much faster. So let's print this to the console and restart our client, and this time try it with our client here. Here the expectation is that when it sends the whole string test, that it will arrive in fact usually in one piece. There is no guarantee as mentioned, but at least, and you see it arrived in one piece, but at least it is likely in such a synthetic scenario. If we would have delays over the internet, then of course you could not rely on anything. It could arrive as 2 letters and then the other 2 letters with a delay in between. The IP protocol can break packages up into smaller packages when needed. So as said, ideally one would need to have some sort of buffer which reassembles the data, and then only once the data are complete sends them further. So are there any questions? Again, since we have now seen how this works in Qt, as I guess you have noticed, it is a bit more elegant than how it is done using the old school Windows API. But at the same time, Qt has quite some additional overhead, so there might be reasons why one might want to do it as low level as possible. So I'm waiting for questions if there are any. Okay, since there don't seem to be any questions, then let's continue with our lecture. So the socket communication, since it happens over network, is very flexible, as you can communicate with pretty much any device across the whole planet. It, however, has, as already mentioned, quite some overhead. It is not very fast, and it has limitations like the mentioned one, that it only supports either a data stream, or you can send unreliably individual packages and just hope that they will arrive, which means you would need then to have some own means of resending lost packages and keeping track of reassembling data packages which have been broken up into smaller chunks. So if you want to communicate between applications on the same machine, on the same computer, there are much more convenient ways of doing that. They are called pipes. So on Windows you have a few inter-process communication mechanisms, in fact, not just pipes. You have also ALPC ports. You can send window messages if you are on the same desktop than your target application, and you can also use shared memory, etc. Asynchronous procedure calls across process boundaries are also possible, so there is quite a lot that can be done. But usually you would want to resort to something that is as universal as possible, and pipes are a very good choice here because they are also available in a very similar fashion on Linux. A pipe behaves somewhat like a socket, just that it does not go over network. It does not need any network card or any network protocols. It works on the computer directly. On Windows, pipe functionality is provided by a driver, which is a integral part of the Windows operating system. On Linux, as it is just part of the kernel itself. I think the only really reliable inter-process communication mechanism on Windows which is part of the Windows kernel itself is our ALPC ports. Other things like messages between windows already requires the Win32k driver and so on. But since there is basically no scenario where you wouldn't have pipes available on your Windows, let's start with them. So as likewise we have done it with for the network sockets. We will start first with a low-level example using Windows API calls, and once we have seen how nice this works, then we will take a look to use the Qt specific libraries, which provide a level of abstraction which is quite nice. Are there any questions? No questions? Okay, then let's continue. We'll need to create a new project. Click. That VM is broken. The button to minimize everything doesn't seem to be working correctly. So create new project, console application, next, pipe server. The terminology with server and client here is analogous to how it is done with network. So you have a server, you have a client, just that the difference is that the whole communication is not happening over the network, but is just mediated by the specific Windows driver, which is, as mentioned already, part of the operating system, and you can always assumed to be available. So let's add some headers. Unlike for WinSock, we don't need any specific libraries to use pipes. The standard libraries which are usually included with the project for Windows APIs should be enough. So let's start. Our approach will be quite a analogous one. We'll need a handler for our server. In this case we call it pipe. We will need a name for our pipe. So with pipes there are two types of pipes, just pipes and named pipes. So on Windows every object can either be named or unnamed. This also applies to pipes, and if you have a pipe without a name, then it's kind of difficult to connect to it. You could use some other means of communication between processes to duplicate a handle into another process, then communicate the handle value to the other process, and so on and so on. But the typical use case where you are using pipes for inter-process communications, you just give them a name, and then you can easily refer to them and connect to them. So we'll start here again with a loop. In this case it needs a bit less preparation. Again, we don't need to change any to initialize any special components. Like with WinSock we needed to start up the socket infrastructure first. For application here we don't need to do that. We can just start with our function calls. There is a API function called create named pipe, which can be used for that. The first argument will be the name for the pipe, which needs to be prefixed correctly, and then we can, so you need this backslash point pipe prefix, and then you can specify the name. Let's go with my pipe. And then we need to specify a lot of parameters. So first of all, we want to have read-write access, so keep pipe access duplex. Then what else? The nice thing about pipes is that you can in fact make them work in the granularity of messages, meaning that if you put two messages into a pipe one after the other, even if they are very short, on the other end each call to read on the pipe will give you only one of the messages. It will not block them together into one larger chunk. But to do this you need to enable this message mode, pipe type message. And if we see here, we can also have other message modes like just byte type, which would mean that it was just a stream, and then you have the same problems that you need to somehow reassemble your messages that you have put on the socket. What else you want? Read mode message as well, and we want the thing to be blocking, so pipe wait. If it wouldn't be blocking, then we would need to handle asynchronous operations, which is a little bit outside of the scope to just understand how the mechanism works. So this is something you might want to do in your application later on, but it's not something that you need to do right now. So the next thing what you can specify is the maximum amount of pipe instances with the same name that you want to allow, which in this case we'll go for unlimited pipe unlimited instances. Then we need to specify a buffer size, so I already have here a preprocessor definition for the read buffer and again for the write buffer. Default timeout we'll set to 0, so it's up to the client to time out. And the last thing are security attributes, which you might want to set if you want, for example, if you want to create a pipe in a service and connect to it with a application which does not have administrative permissions, then you would need to set the security attributes to allow for such a connection. If we are connecting between two applications which have the same level of privilege on the system, then it is not necessary to change those presets. We can just go with the defaults by specifying null here. The next step, of course, will be to check whether we have created the pipe successfully. So if pipe is an invalid handle value. So if it's, by the way, the invalid something values usually are just -1. So the idea is somehow that 0 kind of means uninitialized or not yet tried, but if you get -1, then it indicates to you that something definitely went wrong. And usually this would not be a valid value anyway, so it's usually anyways outside of the useful range, so we are not losing any potential values. So in this case, if this was invalid, then we just break. Then we don't need the additional brackets here. Good. So now what we want to do is to wait for a client to connect. So connect. As you see, it is not as identical to sockets as one might expect from it being as well a client-server mechanism. In Qt it is much more similar, but in the Windows API it's slightly different. The main reason is that you don't have a thing like a listening pipe. With sockets you have, but with pipes you don't. With pipes you can create a certain amount. You can specify a limit here or unlimited of pipes, which will all have the same name and all will be waiting for an incoming connection. And and then for all of them you would need to wait to find out a way to wait on all of them. One would be to create one thread per pipe which would just wait. Another would be to use an asynchronous wait scheme to call this connected named pipe and then just continue to call it for the next and the next pipe. And the idea is that when a client connects, the system just picks one of the not yet connected pipes on the server side and connects the client to that pipe. And then it is the responsibility of the server to quickly enough open the next listening pipe so that the next incoming client connection can be handled. And usually, since it is not expected that you have a huge amount of clients connecting to pipes, this works good enough, even with just one pending pipe. In case, of course, of a network scenario, you might have thousands of clients connecting per second, so such an approach would not be reliable enough, hence it's not used, obviously. The best practice with regard to the amount of pipes of pending pipes waiting for a client connection is to create as many pipes as your system has CPUs, because then you can reasonably assume that even in a scenario where there are many clients connecting, you will always be able to create the next listening pipe before a task switch. And another thing to keep in mind here is that when you try to connect to a pipe and this pipe and there is no pipe ready to receive the connection, you can in fact wait for a server pipe to become available. So if you do that on your client side, then you can ensure that even if the server would be overloaded intermittently, that instead of connection rejected, you would connect just slightly later. So we might take a look into that later on. So we have our create pipe, connect named pipe. Then we want to specify here our pipe. The second argument, the overlapped parameter, would be used if we would want to somehow asynchronously wait for multiple pipes at the same time. But since we said that here, where the pipe wait, that it is a blocking type of pipe, then we just specify null, and this here will wait until it's connected. And if it's successful, then it will return true. If it's failed, it will return false. There is, however, a catch. There is a scenario where it can return an error, but then still end up connected. So we need to be able to handle for that. So let's create a variable which will indicate whether we were successful or not. For then connected. And first of all, if this is true, then true. Nothing else to do. But if it's false, then we need to get last error and check if this is error type type connected. I have no idea why it can successfully fail, but apparently at some point it was implemented this way, and now it's a standard. Anyhow, so if this is false, if not connected, then continue, because nothing else to do. We just try to create a new waiting server pipe as quickly as possible. If we managed to connect it, then we can either handle the pipe ourselves, or we can try to create a thread like before, and then let the thread process the request. And I think since we want our server to be able to receive more than one connection, we should do that. So let's quickly go to our TCP server and steal the function definition, which is pretty trivial anyways, but there are like details which are good to just get from somewhere else instead of having to remember them. Generally I find it convenient to not remember things which can be just looked up somewhere, and given that there are quite many different APIs and frameworks, just trying to go by memory for all of them is cumbersome. So the best is to just know where to look things up and only remember whatever you are working on right now. So again, we have here our create thread, and also unlike before with sockets, the connect here does not create a new object. The existing pipe just becomes connected, which reminds me that here we should close it. In case of a failure, we still need to close the object, otherwise we would have a resource leak. Okay, and of course here a pipe, and the type handle is again one of the types that you can just cast to a void pointer. Internally it is here in this case again just a normal void pointer. There are some configurations where they can be kind of, how to say it, they use a sort of dummy structure to make casting from and to void not implicitly possible, so we always need to do it explicitly, which in some scenarios helps you to avoid bugs, but it's not something that is necessary, and also it depends on some configuration aspects whether it will in which way it will behave. So, but going back to our client procedure, so when we have an incoming pipe, the client thread will be started and it will run as long as the client connection is connected, while the main loop of our main thread will keep receiving new incoming connections. So we need a for loop again without any conditions so that it runs forever, and we use this time the read file function, and this is something that mostly resembles how pipes are made on Linux, where everything more or less is a file object, and here on Windows pipes also just work as device objects. You can read and write to them with the read and write file function, which usually you would just use to read and write normal files, but generally speaking you could read and write also to other devices which expose the right interface. So you could implement an own driver which has a special NT-path, and you can open that and then read and write to your driver, for example. This also, by the way, how internally that was at some point just implemented with their own driver that provides the pipe functionality. So we need a buffer. So the read function is quite similar. Number of bytes to read, size of buffer. Then we have number of bytes read. What was it? I think a double word. Yep. Word. Read vitesse equals 0. Reference read bytes. And again, this overlapped structure in case we would want to do it asynchronously, which we don't. So if read fails, then we break our loop and close handle on our pipe to not have any unreleased resources. Otherwise, we just send it back using write file. Again, we need to specify the file, or in this case the pipe. Then our buffer. Then how much to write. So here we get the read bytes value. Then it tells us how many bytes it has actually written. So if the buffers are full on the receiving end, then it might send just a portion of the package. So here this, and again we have a null for our thingy, and if this fails, then again just break out. Okay, that should be it. We can run it. We don't have anything to test it with, unfortunately. We could. I think we could. Let's, I think putty. Yes, we need to return a value here. I think the putty client can connect to pipes. So let's use it to try it out. Let's quickly just copy the putty onto the virtual machine. Putty, zack. Okay, so we have our putty. This one doesn't say pipe. I think you have to select serial and then the pipe name, if I remember correctly. Let's put a breakpoint here so we see if we have connected. Serial. Yep. it works. It's a bit counterintuitive that you don't have like a type pipe. You only have serial, which would actually be intended as the serial port on the computer. But since the serial port is again implemented by a driver and it just presents itself as a device to which you can read and write and which you can open with OpenFile, effectively it is completely addressable the same way as a pipe would be. It has some more control codes which you would use to set the data rate and other parameters of the port, but a pipe doesn't have any of those parameters. It will just fail those requests, but PuTTY is apparently tolerant enough that it will not care. Okay, so here we remove the breakpoint and we run it, and then we put here a breakpoint so that we see what we type. Let's see how fast I was with typing. Well, 1 letter. I wasn't fast. I pressed a few letters, but we only got 1, and now we will each time getting 1. So unfortunately, it is not fast, but as you see, we are getting our echo. Yeah. So this works nicely, and when we close this, we should then go into this breakpoint. Because the pipe should be closed, and it is. So at this point our thread terminates. So what we will do now is we will implement the same thing. Well, we will implement a known client, and then we will implement the same thing in Qt. So one thing after the other. Qt console application next. Sorry. We wanted the non-Qt version first. Pipe client, create. Okay. Let's go to our pipe server and copy our includes. Zack. Okay, so. Rightio. So as said, it is quite simple, quite a simple thing. We need a handler, pipe. Oops, handle is all capitals, and we just open a handle using either the open file or the create file function. The create file function, unlike its name would suggest, does not always create a new file. What it means is it creates a file object. So if you can use create file to open an existing file. Why they had these two different names, I don't know. The behavior, whether you want to overwrite or not an existing file, or whether you want the function only to succeed if the file name already exists, is to be specified in parameters for the create file function. So create file, file name. We will just copy our file name from here. File name, Zack. Then we will specify the access mode, so we want generic read and write. So we want to read and write from the pipe. Then share mode null. It's not shareable. With a file you could specify, for example, how to, so if you open the file, then the system knows that some application has opened the file, and unless you close it, it will remain in this open state. And you can specify how you want the operating system to respond to another application trying opening the same file. And you can either say that it cannot open it in any way. You can say that it can open it but only for reading, which is the default. So if you open the file for writing, then you might edit it at any point in time, but you allow others to read it still. Or you could say that if of course if you open it just for reading, then it's fine to allow others to read it as well. But you could also open it for writing and still allow others to open it for writing also, which in special scenarios might be useful. That is why you have this share mode parameter, but for our case it doesn't matter. Then we don't need security attributes. They would be mostly interesting when creating a new file anyways. Then we need to specify the open mode. So they create this position, which in fact kind of makes a difference whether it is an open file or a create file with regard to the file system or other object. So here of course we want only open existing. And we have a few others. So we have create new means it will create a new file. It will fail if the file already exists. Create always will create a new file, and if the file exists it will delete it and then create a new one. Open existing will open an existing file and fail if the file does not exist. Open always will open an existing file and open a new file, create a new file and open it if it doesn't exist. The difference I think to create new is that open always will keep the file content intact, while create always, if the file exists, it will truncate it to 0 size. That's why there are two. And what's the last one? Truncate existing. Yeah, this one will be kind of, the file must exist, but it will be truncated, if I remember correctly. If not, refer to the manual. Okay, so special flags we don't need, and template we also don't need. So that's it. And here we can check whether we had an error. So if there is no server with this name, if build handy value. So if there is nothing to connect to, then we just bail out with an error. There is another scenario. So it might not not have an error. So it might not be an invalid state, but it may still not have connected correctly. So for example, if it's busy, so we can if check the get last error function. So if this is ungleich error pipe busy. So error pipe busy is so if it's not error pipe busy, then something went wrong and we cannot recover from it. Otherwise we can. So now, so at this point we were able to get successfully a handle. The error was not that. So the error was that pipe is busy. If there would be anything else, then we would bug out. So we should at this point then close the handle, but let's do that later. So what now we want to do is we want to check. Wait. Error handle. We can. There is a small bug. So first of all, this will always fail. So how to do that best? Let's put this into a loop, and let's put this into a loop. Right here. So if this is not, then we break because we have successfully connected, and if it's an error, so we don't have a object, then if it's not this error, then we break completely because we cannot continue. And if it is this error, this means we had no server instances ready, but in principle there should be some, so we just need to wait. And we can use the wait named pipe function. We need to specify the name, and what the function does is it will log for how much time we want to give it. Let's say 20 seconds. It's in milliseconds, and if it returns true, it means there is now a pipe available. If it returns false, then it means that the timeout passed, but no new instance became available. So we would expect this to very quickly exit, and then we repeat the loop and then try again, and then hopefully connect. Okay, so at this point we have it connected, as we have just broken out. We could actually improve that also slightly. We initialize this, and we will always break. and here we just check if it's invalid, then return. That is more elegant. Okay, so at this point we know we have a pipe successfully connected. So let's configure it. Set name pipe handle states. Pipe, comma, mode pipe. Right, that wants a pointer. Read mode message. Pipe mode, and the rest doesn't matter. So we could set our own buffer size, but since the server already set the buffer size, we don't need to do that. So we just pass here a null values, and now we can write file. Pipe buffer. Oops, my copy failed. Pipe test4. I mean, this is not very elegant. I should create a variable and so on and so on, but for quick it's fine. Bytes, comma, overlap to null. Okay, so we write, and then we use read file to read the response. We just need a buffer. And close handle to disconnect from our pipe object. Breakpoint passed. The server is still running, so let's run it. And voila, we got our message back from the server. So it works, and then of course once we allow the socket to close here, our client process thread terminates as well. Good. Any questions? No questions? Okay, if there are no questions, then let's continue with so since we have the server running, then let's continue with creating a Qt client and connecting to it. Creating project, Qt console application, QPipe client. Great. And here we also need to add the networking component. It is a little bit counterintuitive since it doesn't have anything to do with network, but Qt's rationale was that they want to use the QAbstractSocket class as a base for the pipe communication as well. So they have just put this IPC functionality into the package which contains otherwise network communication. So this is a bit annoying, but it is what it is, as one would say. Okay, so again we will start with the nice way. We'll create a class. The thing needs to think. Okay, it's a C client derived from Q object. we can start by just copying everything and then we just adapt it. Then you will also see how similar the mechanisms are, especially when using the Qt API. Pipe client, C client, main, new C client. Right, so we want to change this to Q local, Q local socket. Client, what is this complaining about? Yeah, this should be on the only line going to change. Connect to server, and if I remember correctly, the thing strips the Windows specific prefixes, so we just have to say my pipe. I might be wrong, but I think I remember correctly. And that's it. As you see, it's quite identical. You just have a different connection command, but everything else stays the same. And that is, as already mentioned, because the Q local socket is just derived from QIO device, like the normal other sockets are as well. So yeah, that's that. So let's run it. And we should expect here on the console to see our test string coming back to us. Yep, and voila, it works. So the next step, of course, will be to implement a Qt server, which will again be just mostly a copy of our existing one, just with very minor changes. Create a project. Q pipe server, create. Okay. Add class. Okay, the Visual Studio needs to think for a minute. I think we have too many Visual Studios open. Class server Q object sec. Okay, right here. So Q local server Q local socket local server local socket. Okay. Right here. And then the other one, this one. Here. server listen, and here we just need to specify the name of the pipe. That was my pipe, I think. And of course here q local socket, and here as well, and here and there, and that's it. Okay, let's run it. Then we'll run our client again, and we'll expect on both consoles to have our test message printed. Okay, that's that, and our client. Still starting up. And voila. So as I think it becomes apparent here, it is quite a bit more convenient and straightforward to use Qt. It's also quite nice that you don't need to manually manage any additional threads, and being able to have all your program logic in one main thread and then just signals coming in with the data packages. This is quite a convenient thing. One thing that we have not looked into here yet is the use of UDP sockets. So as I mentioned initially, the TCP protocol ensures that your data stream is intact and that packages will be delivered, or the whole communication will be aborted if enough retrace fail. UDP, which stands for User Datagram Protocol, is a means to send single packages over a network without any sort of guarantees of any kind. So you can just send the package on the network, and if the network is okay, it will deliver it. If something happens on the network, it will just drop it. So if you are using UDP, you will need to manage your own resends and timeouts and everything. It is quite similar to what we have already done with the TCP, just that there is no such thing like listening. You just open a socket, and then if data come in on the socket, you just receive them, and you can retrieve the information from which IP address and port the data were sent to your socket. So even the tracking of individual clients you would need to implement manually based on the IP addresses and port combinations that you are getting communicated by the operating system from where the information has come. This is usually not used very much on scientific devices. Most instruments will just use TCP connections, simply because of the simplicity from the operator's point of view. UDP communication is mostly used if you want to communicate over the network, and you want some special means how to you have some special requirements, so something that you could not implement using UDP. And examples of that would be, for example, something that you could not implement using TCP, I mean. And the typical examples here would be if you would have something where the automatic congestion control mechanism of TCP would kind of interfere with what you want to do. An example could, for example, be a video streaming or audio streaming. If you don't care that sometimes the data will be corrupted, but you care to have the lowest possible latency, then sending your data as UDP might show advantages. Other use cases would be if you have some network address translation on your network and you want to get through it in, let's say, not the way that the manufacturer recommended. This is called net traversal, and it usually works by exploiting net characteristics and using UDP packets. You could also use UDP packets if you want to implement some own congestion control protocol. So if you have a network which is either very fast or very slow, then the default presets that are used by Microsoft's TCP implementation would not be suitable for you, in which cases you could opt for using an own self-implemented protocol. And that might be interesting in some scenarios. Generally, I think for most users in the lab, this will not be something you might have to deal with. Although there is a use case which might be worth considering, namely if you would want to communicate with an Arduino or some other very basic microcontroller. TCP as such is already quite complicated, so if you really want to save resources on that hardware, then what you could do in this case is you could only use UDP frames and communicate only in single UDP packages, which you send back and forth, and then check if you don't get an answer for a request, and you just send your request again and stuff like that. So of course nowadays with the price of more advanced microcontrollers being in the single euro digits, like the Pi Zero, then really there is no need to use some very old 8-bit microcontroller to communicate over network anymore. You can just use something like a small Raspberry Pi, and just then you have a full Linux stack, and you can communicate with it with whichever protocol you want. But since it is a integral part of networking and we want to have a good understanding of it, I think the next thing we should take a look on would be this UDP communication. And since we don't have much time today anymore, we could actually take a look. Just start with the Qt implementation, and if we have time left, then we will look for the old school Windows implementation. So let's quickly do this. Yeah, let's create another client. One downside here is that I think PuTTY cannot communicate over UDP, so we need to create both clients. Well, I wanted to create both client and server, but technically UDP does not have the distinction between a client and a server. Just a peer in the network opens a socket on which it receives messages, and it sends messages from that port to other clients, and that's the whole extent of it. There technically any site can be a client or a server. For our particular use case, we can still opt for calling one of them the client and the other one the server, because one is sending a request and the other one will be just receiving it and sending it back. So I think that is good enough. Or we call one of them client 1 and the other one we call client 2. Yeah, that is probably a better idea. So to avoid confusion, QUDP client 1, and then we will in parallel create another QUDP client 2. Or we'll actually, the other option is that we just copy it and then use just slightly edit it. That would also work. Of course, we need our network module, since this time we will be using proper networking. So this is client 1, and now let's quickly create client 2. Create new project. Next, QUDP client 2. Great. Okay, next, network, next. Right here, so we have our two clients. Add class CUDP, just the client, or socket. This time let's just call it csocket. Our client 1 will kind of have more a server role, so let's not call it a client anywhere. Okay, so I forgot to say to derive it from QObject, but that's not a big problem. We can quickly make it right here. So we have this, then here our construct object constructor, and let's just copy some things to main sac. Okay, so new socket, okay, so let's think. Here we will need to have again a few slots. Void on, we'll call it we'll call it on datagram, which will be triggered whenever a package is received by the UDP socket, by the underlying UDP socket. Then we will need a socket q which we need also to include here the right header for UDP socket p socket. Okay, and now to the content of our client. We should give this an argument so that we can give it a port. Before we just have hard-coded the port. It doesn't matter, we can also hard-code it here. Let's not complicate things unnecessarily. So create new. Bind to a port. Let's go with 1, 2, 3, 4. Connect socket, comma signal ready read, comma this, comma on datagram. Slot on datagram slash. Okay, and in our slot we need a buffer. I think not necessarily. You can also use the read all function. No, we cannot. We need to use read datagram because we want to know where it was sent from, and this only accepts a buffer. Okay, char buffer sac. Okay, so read datagram buffer comma size of. Here the return value is either so 0 in there was nothing, -1 there was an error, and positive number is the amount of bytes read. Now we will get a qhost address and the port from which it came. So qhost sender and int 16 port, reference sender, reference port. Right here, and we will print to debug what we have received, and to not print any garbage, we will int then we'll set the last byte to 0. This way it will be a 0 terminated string that we read, and of course we want to send that data back to our other end. Write datagram data comma len comma host address and port. Okay, so this is already done. We can run it. Okay. And the other client we will implement slightly differently, just to make things more interesting. Yes, we need to tell the firewall, of course, that it is allowed to access. Okay, so we of course need again our include QUDP, QUDP socket and the socket. Okay, we create a new one. We bind it to port 1, 2, 3, and this time 5. The ports must be different because you cannot have two ports, two sockets connected, listening, bound to the same port on the same computer. So here we will need a different number, and then we will create some data which we want to send. So let's say Q byte array test is equals test, and then Q host address 2 0.1 Q16 port. Here we need the port of the other socket, which is 1, 2, 3, 4. You see the difference? 5, 4. Just here incremented by 1 to not have a conflict, and we can send it. So socket, right, datagram. We can use this Q byte array, comma host 2, comma port, and it will send it. And now we want to wait for the data to be written. So instead of just sitting on a signal, we will here wait until there is some ready read that was signalized. And now I can go back here and just copy this portion of the code with one difference. So we receive it. Okay, we have reused port, so this is not good. Port, yeah, ports 5. Right, and here we want to qdebug what we have received. So let's run it. That might fail the first time if the firewall is in the way. So that is might be to be expected. Although I think it might also work because on localhost the firewall, yeah, it worked. So if the target is the localhost 127.0.0.1, then even if the firewall would be set to block it, it normally would not, since apparently there is when designing the Windows firewall, they decided that you don't need the ability to block localhost communication for some reason. So yeah, as you see, it also works. The package arrives, and the most notable difference here really is that you don't have any sort of connection establishment. You just have your socket with your port, and you send to another socket on another port, and the data either arrive or not. Since we were testing on the local machine, there is no expectation of things not arriving, in fact. But of course, if we would be testing this over a real network, then and sending more data, then we would expect some data to be dropped at some point if we have the data rate dialed up too high. Yeah, but that's that. And since we are running out of time, then I think this is a good point to stop. If there are any questions, you can ask them. I will stop the recording now and upload all the projects to Moodle. There won't be any homework today, since I saw on Moodle that there's quite a lot of homework not yet been done. So yeah, that's that. I will stop this.